The following program is brought to you by Caltech.
Well, good afternoon. I'm Gary Stupien, class of 61, session chair for this session. And today we are going to hear from Professor Sunil Golwala. He's a professor of physics and director of the Caltech Submillimeter Observatory. He received his undergraduate degree at the University of Chicago and PhD at Berkeley. And he's been at Caltech since 2000 and on the professorial faculty since 2003. And he's going to talk to us today about dark matter. This is one of the big mysteries in physics today. There wasn't any dark matter when I took physics at Caltech, but to my surprise, there is now.
All right, thank you for that nice introduction. So I'm going to tell you about the hunt for dark matter, why we think there's dark matter in the universe, and how we go about trying to detect it directly. So I'm going to start off with this really basic Phys 1A level type of problem. The question is, how do you weigh things? How do you figure out how much mass something has? And here on the Earth, we might weigh things by comparing it to a reference mass. And the reason that works is because we're on the Earth, right? The gravitational force acting on the reference mass is the same as the gravitational force acting on the thing you want to weigh if they have the same mass. So in that way, we rely on the gravity of the Earth to tell us how to find out the masses of things. Another way you can weigh something or find out its mass is put it on its spring scale. And the weight, the force of the Earth on the apple causes the spring in the spring scale to compress and turn the needle. So again, it requires you to be on the Earth. You need the gravitational force of the Earth acting in order to do this measurement of the mass, the weight, and therefore the mass of the apple. So the obvious question is, how do you weigh a galaxy? You can't do it directly using a spring scale. But you can do it in a similar fashion by measuring, by measuring acceleration. So what we do is we measure the velocity of the gas in the stars going around the center of a galaxy. And you all know also from Phys 1 that if you take a spectral line, say atomic hydrogen's 21 centimeter emission or optical spectral lines, if the source of that spectral line is moving away from you, then that line is redshifted. It's moved to lower frequency, it's made redder. On the other hand, if the source of that line is moving toward you, it's blue shifted. The frequency is increased or it's moved to higher energy, higher frequency. So we can use that. If we can measure these velocities, then what we can do is use the relationship between the centripetal force to tell us how much force must be exerted to make those things move in a circle. So the centripetal force is given by the mv squared over r. That tells us the force that's exerted by this athlete to keep the ball moving around in a circle. Similarly, that gives us the force that's required to make the stars and gas move around in a circle around the center of the galaxy. So we just require centripetal force equal gravitational force. That tells us how much mass is enclosed at the radius of the stars or gas that we're looking at. So this is a lot like the equation that we use for when we want to measure the mass of something on the Earth. We're using gravity to infer, we're using speeds here instead of spring scales to infer how much mass there is. Okay, so this was first done by Vera Rubin in the late 60s and early 70s by looking literally at the velocity, looking at redshifts and blue shifts of light from stars and gas as a function of distance out from the center of galaxies. So here's M31. The vertical scale is the velocity. The horizontal scale is the distance here projected onto the sky. And what she found was that the velocities went up and then they flattened out. Okay, and that's an interesting thing, and I'll explain why in a second. But let me just, as an aside, let me just note that even though galaxies had been observable since the 20s, 30s, it was only possible to start doing these measurements in the 60s because of better light detectors that became available at that time. Then you could take spectra of many, many points along a galaxy and make these types of measurements. So here's one of these types of measurements. So the image here, the black and white, is the galaxy NGC 3198. That's what you see in stars. And then the contours here are the 21 centimeter emission from atomic gas. So this is gas that extends out well past the stars. And you can measure both of them to figure out the velocity as a function of radius. And we again just use centripetal force is equal to gravitational force. So this is again these types of measurements where you measure a velocity that goes up and then it flattens out. and it stays flat to well past the edge of the visible optical disk of the galaxy. If you calculate what you would expect if the disk of stars was all the mass that was there, you should expect the velocity to go down. So it's inferred that there's some sort of halo of stuff, of additional matter, that's providing the gravity so these stars and gas can go around in a circle that fast at that radius. You can convert this into a mass measurement. So now this is the mass enclosed as a function of radius. And you see the disk goes up and then just stays flat because there's no more disk once you get past about here. And so this is the inferred mass enclosed of the entire halo of the galaxy. So this is the matter that must be there in order to make the stars and gas move in those circles so fast. So this is why we think there's dark matter, is because of these kinds of measurements that say there's a lot more gas there, a lot more matter there than we think we can account for in the disk of the galaxy from stuff that we see. Here are some quotes from a couple of Rubin's papers. Clearly she points out one of the first people to notice this, and then she says that galaxies contain massive halos extending to large radius. Most galaxies exhibit rising rotational velocities at the last measured velocity. Only for the very largest galaxies are the rotation curves flat. So they're still actually rising. They're not just flat. They're not flat in most cases. And the mass is not converging to a limiting mass at the edge of the optical image. The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. So this is what our picture of galaxies is these days. You have the thing that you see in pictures, the optical galaxy, is this small thing in the center, but then there's a huge a sphere of dark matter that this thing is sitting in, non-luminous matter, we call it dark matter, and we don't know what it is. Okay? So another person who really kind of invented the idea of dark matter and pushed it was Fritz Zwicky, who was in the astronomy department here for many years. His first paper is totally inaccessible. It's in some German journal with a very strange title in German. But I was able to find the second paper, which was from 1937 from Astrophysical Journal, using measurements that he made using the 18-inch Schmidt telescope on Palomar Mountain. So there he is in a posed picture. And what he did was he looked at a cluster of galaxies called the Coma cluster. This is one of the nearest very massive clusters of galaxies. And all these dots here are individual galaxies. And the scale here is 1 degree, 2 degrees. So it's a very large object on the sky, bigger than the moon, but it's so faint that you can't see it with your eye. So what he did was he measured the velocity along the line of sight of each of these galaxies by using redshifts again. And from the speeds of those galaxies that he inferred, he could calculate how much mass has to be enclosed, just like we did for an individual galaxy, but now for a huge assembly of galaxies. And he says that the mass to light ratio, that's the ratio of the total mass there to the total light there in terms of solar masses divided by solar luminosities, must be about 500. Whereas for a typical stellar system, it's only about 3. So again, he's pointing to the fact that there must be some kind of additional matter that's not in the form of stars that's explaining these large velocities. And he says the discrepancy is so great that a further analysis of the problem is in order. And we've been doing that analysis for the last 80 or 90 years. Okay, so now I'm going to digress a little bit on things that that matter can do. So obviously we use the term dark matter to describe this non-luminous matter, and I'm going to tell you a little bit about why we think it's not anything like the matter we see normally. But I have to digress a little bit to talk about gravitational lensing. So what you're seeing here is a simulated image of taking a galaxy, a thin stripe of a galaxy that you see from the edge on, and running it behind a black hole, or you could think of it as moving the black hole in front of the galaxy. And this distortion you see is because the black hole's gravity is so strong that it actually bends the light. The black hole curves space-time around it, and that curved space-time causes the light to follow paths that don't appear to be straight. So this is a classic example of what this looks like. This is a massive cluster of galaxies called Abell 2218. The cluster is all of these foreground galaxies that look normal-shaped. But then you can see from the background there are these arcs. What those arcs are individual galaxies way behind the galaxy cluster whose light has been bent and stretched out into these arcs that sort of make circular contours around the galaxy cluster. And what's happening here is this kind of thing, where you take your background galaxy, the light normally would pass through the cluster, but the light that's going in other paths is actually getting bent and then comes to your telescope. So you think that the galaxy is here, and there's a copy of it here, and you can see also there's some distortion in the image. So this is called gravitational lensing. And one of the kind of most visible manifestations of dark matter is this object called the bullet cluster, which consists of a cluster that's formed by two smaller clusters merging together and passing through each other. The optical image just shows you the actual galaxies themselves. The blue image tells you the mass that's been inferred from gravitational lensing. So the curvature of those arcs can tell you how much mass is enclosed and how much mass must be there to do the lensing effect. So the blue gives you the total mass from lensing, and then the red is the gas from X-ray emission. And what you can see that they're displaced. And so people have done simulations to figure out how you can get something like this. And here's the simulation. Again, blue is dark matter, and red is the gas. And you can see that as these objects pass through each other, the dark matter is not collisional, it doesn't slow down, whereas the gas interacts with itself and slows down. So you end up with these two displaced objects that are the gas mass in red, but then the dark matter kept going. So this is one reason we think that this additional non-luminous matter, the stuff that we call dark matter, is not anything like the matter that we normally talk about, because it doesn't slow down like that when it collides. Okay, so why do we have to have something that's besides normal matter to be dark matter? So as I explained, it has to behave differently in order to explain something like the bullet cluster. And then there are a variety of measurements that tell us that, in fact, only about 1/6 of the total matter in the universe can be normal matter. We can measure the abundances of light elements today and infer from that the total amount of normal matter in the universe. And it's about a factor of 6 too low to explain the total mass that we're able to measure through lensing measurements like I just talked about and other measurements. And then there's the cosmic microwave background, which is this backlight from the early universe. Jamie Bach talked about it this morning. And there are fluctuations in the cosmic microwave background. And those fluctuations tell us about both the fluctuations in the total amount of normal matter and the fluctuations in the total amount of non-luminous matter. And we see that the fluctuations that are there are too large for them to be made of normal matter alone. There would be no way to form the kind of gravitational wells that cause those fluctuations. And also, those fluctuations are actually too small to produce all the structure we see today. So there had to be something else that was fluctuating, whose density was fluctuating at that time when the microwave background was released, and grew into the structure we see today, galaxies, clusters of galaxies, et cetera. And it works out well if we have a total amount of matter that's about 6 times the normal matter. So 5/6 of the total matter is in dark matter. There are other candidates. Primordial black holes have been put out for years as a candidate, but these things, they would satisfy all the above criteria, but they're not particularly well motivated. So we're kind of motivated to think of some new particle that might make up this so-called non-luminous or dark matter. Okay, so why do we first go to a new particle? Well, there's a strong history of doing this kind of thing in physics. So there was the problem of nuclear beta decay back from the 20s and 30s, where it was observed that some nuclei would decay by emitting an electron, and if you looked at the energy spectrum of the electron, it was continuous. But you only saw the electron in the nucleus. Again, remember your Phys 1a, if you do a two-body interaction like this, the electron should come out with just a single well-known energy because there's only one particle for it to recoil against. So this was a mystery, and people started thinking, oh, is energy not conserved or something like that? So Wolfgang Pauli wrote this famous letter trying to propose a theory. I'm sure many of you have seen it before. It's titled, he's writing to a conference and he can't make it because he has to go to some sort of ball or event. And he says, "Dear radioactive ladies and gentlemen, I've hit upon a desperate remedy to save the law of conservation of energy." So he wants to keep the law of conservation of energy. He says, if there could exist electrically neutral particles, which I will call neutrons, these later came to be called neutrinos, they are not the neutrons that you think of in the nuclei, the continuous beta spectrum would then make sense with the assumption that in beta decay, in addition to the electron, a neutrino, is emitted such that the sum of the energies of the neutrino and electron is constant. So you get to save conservation of energy. But so far, I dare not publish anything about this idea and trustfully turn first to you, dear radioactive ones, with the question of how likely it is to find experimental evidence for such a neutrino. And it was hard. It took 30 years to find the neutrino. I admit that my remedy may seem almost improbable because one probably would have seen those neutrinos if they exist for a long time, but nothing ventured, nothing gained. So, dear radioactive ones, scrutinize and judge. So this hypothesis was put forward in the 30s, and it took 30 years to demonstrate that the neutrino exists. So I think there's a good precedent there to follow, that we need a new particle and that we may have to wait a while to find it, but it's probably going to be there. Okay, so what does this new particle need to do in order to explain what we see? It has to be produced in great abundance in the early universe. It has to be massive enough today that it's slow. It has to actually collapse into galaxies and clusters of galaxies, actually forms the bulk of the matter in them. So it has to slow down enough. It has to have very weak interactions with normal matter, so we wouldn't have noticed it yet. This is exactly what the neutrino does. It doesn't have very strong interactions with normal matter. It has to be stable, so it's still around today. And you can satisfy all these properties if you have a particle that weighs around 10 to 1,000 proton masses, maybe a factor of 10 more in either direction, and interacts by something called the weak force. This is the force that actually explains nuclear beta decay. It's a very weak force, and therefore it's possible for this particle to have been around us all the time but not interact very much. And you can actually do a calculation that shows that it could make up about 5/6 of the dark matter today if it has these properties. So these things are termed weakly interacting massive particles, or WIMPs. They're not in the standard model of particle physics. They're not explained by the physics that we know about. For about 2 or 3 decades, supersymmetry, which is one model of what physics beyond the standard model is, has been kind of viewed as the best predictor of what the dark matter might be, and it, in fact, does predict a dark matter particle in most cases. It's being tested by the LHC. LHC is trying to produce supersymmetric particles, which means we might make those things in the laboratory. But the LHC hasn't produced anything except the Higgs boson. It hasn't produced any surprises. So there are many other theories nowadays that can also explain dark matter without requiring supersymmetry. So here's so this little chart was actually made back in the 80s, and it's a bit of a joke on the idea of supposing new particles to explain things, observations. And it's titled A New and Definitive Metacosmology Theory. These guys were all graduate students at Princeton at the time. They're all now tenured professors at various places. It says a new particle is envisioned, which is demanded by supersymmetry, good example, right? Or maybe isn't demanded but would be nice, is cooked up just to make everything okay, is bunk but everybody knows it, or nobody's telling the astronomers. And, okay, I'll follow this track, is massive and weakly interacting. It could be hot, cold, lukewarm, or dry, clean only, and stable, and just sits there. No. Causes formation of stars, galaxies, QSOs, clusters, pancakes, French toast, nothing. And still accounts for biased galaxy formation, mass extinctions, Ronald Reagan's popularity, or nothing, and implies the existence of various things, including a professor at Princeton at the time, Jim Gunn, but violates all kinds of observations or federal law. Still, it has been detected, never, or maybe in various places that no one can reproduce. So yeah, while there's a good precedent in physics for supposing new particles, we tend to be very generous with that supposition of new particles, and most of them don't actually turn out to be true. Okay, but let's talk about how you might go looking for this weakly interacting massive particle. One method is actually by producing it. So when you run a quark into an antiquark, and these are in the proton and antiproton, such as at the Large Hadron Collider, so these are 3 of the detectors at the Large Hadron Collider, you can produce stuff. And in fact, you might be able to produce the dark matter particles chi. So what you would look for is a collision where stuff comes off and you miss it. So you see missing energy or missing momentum in a collision at the LHC. And so searches for that are very active at the LHC. Another way you can do it is take that diagram and turn it around. So now you take dark matter and run it into itself, and it produces stuff. That stuff might be electrons, it might be muons, it might be gamma rays, it might be gluons, it might be all kinds of things. And this actual process has to happen in the early universe in order for the dark matter to exist. There has to be creation of dark matter and annihilation of dark matter in the early universe. So we actually have pretty good predictions for what the amplitude of this, the rate of this kind of effect should be. And so what you expect to be produced is all kinds of exotic things like antimatter, positrons and antiprotons, neutrinos, and also normal matter, electrons and protons. So a number of experiments in space, the Fermi Gamma Ray Space Telescope, the Alpha Magnetic Spectrometer on the space station, and also on the ground, IceCube, which is an observatory in the South Pole ice that tries to detect neutrinos, are looking for these kinds of signatures of dark matter being annihilated in our galaxy and producing these products. But in this talk, I'm going to focus on direct detection, which is where we take that diagram and we turn it 90 degrees, and we expect WIMP dark matter to scatter off quarks and nuclei. The WIMP flies off and we never see it again, but the quark has acquired some energy. And we want to see if we can see these quarks who've been given energy by a WIMP interaction. And these are pictures of some of the current dark matter direct detection search experiments. Okay, so what might you expect a dark matter particle to do when it interacts with normal matter? Well, we know a lot about dark matter, at least its kinematics, because it lives in our galaxy, and we understand the structure of our galaxy at least at kind of the order of 1 level. So if its mass is around 100 proton masses, we know its speed is only about 300 kilometers per second. That's the typical velocity of things in our galaxy at our radius. That's only 1/1000th of the speed of light. In spite of the small mass and the relatively slow speed, the flux is enormous, 10 million per square centimeter per second passing through all of us all the time. So what we expect is because they're non-relativistic, they scatter in a very simple way. They just run into nuclei like billiard balls. And the typical energy that would be deposited for this mass and that velocity is around tens of keV, kind of the energy of a medical X-ray. It's a standard Phys 1a type of scattering problem. But the rates have already been constrained to be less than 0.01 per kilogram per day. That means that if you have 100 kilograms of target sitting there, you'll see maybe one interaction a day. That's where the upper limits are today. Okay, so we're looking for nuclear recoils of nuclei in a target with tens of keV of energy. They can also scatter off electrons, but they can't give much energy that way. It's like throwing a tennis ball at a moving truck. The tennis ball gets a lot of momentum and it gets a lot of speed, but it doesn't actually get that much kinetic energy. And what we care about is the actual energy we can see. Okay, so why is it hard to do this? Well, as I mentioned, the rates are very low, and the key thing is that there's a whole lot of other stuff hitting any detector you build. If, for example, you just look at your body, there's an enormous number of radioactive decays happening in your body per second, about 4,000 decays per second from potassium and a comparable number from carbon, and you can't get away from those. You need potassium and carbon. And the Earth itself is fairly radioactive due to uranium and thorium and radon. If you are above ground, we're all being showered constantly with particles that are created when very energetic cosmic rays hit the top of the atmosphere and create showers of charged particles, so that kind of stuff is hitting us. So you need to get away from all of this stuff, and you still need to do it with lots of target mass. The energy depositions are quite low, tens of keV, but we need big detectors, so we need to detect small amounts of energy in big detectors. And then finally, as I mentioned before, we need to separate recoils of nuclei from recoils of electrons, which is actually what most of the radioactivity produces. Okay, so what are some good materials to use for these detectors? Well, you want things that are clean and have properties that make them usable as detectors. So silicon and germanium have been used as detectors for a long time because they're very well purified by the semiconductor industry. The purification of these two things is very, very good. Liquefied noble gases are actually very good detectors. Because of their chemistry, they're very hard to contaminate, or if they are contaminated, they're very hard to clean up. I mean, they're very easy to clean up because the atoms of the noble gas don't bind to a lot of the contaminants. For your shielding, things like copper, copper is a very good material because it's very easy to get pure copper, OFHC, and you can actually electroform it, literally use the electroplating process to produce massive amounts of copper and make it extremely pure of uranium and thorium. Lead, surprisingly enough, can be made extremely pure also, except for one isotope, which if you wait long enough will decay away. And then plastics and water actually can be made very clean if you start out with the plastics, if you start out with stuff that's clean of carbon-14, and water can be purified very, very well. So these are kinds of the elements that go into the experiments that we build. Now, nuclear recoil discrimination, there's some really interesting physics here, and it just comes from the fact that if you give tens of keV of energy to a nucleus, it doesn't go very far. It moves very slowly. It moves off at about 1,000th of the speed of light, and it goes tens of angstroms in your target, liquid or solid target. Whereas if you give an electron that amount of energy, which is what most backgrounds will do, what most radioactive contaminants will do, it zips off at a good fraction of the speed of light and goes many microns. So you get a very dense energy deposition for nuclear recoils, which is what dark matter would produce, and you get a very sparse energy deposition for electron recoils, which is what most backgrounds produce. So this key difference is what most experiments use to try to search for dark matter particles. Now, neutrons can also create dense energy depositions because they interact with nuclei, but neutrons are actually very easy to shield, so that's acceptable. Okay, so nowadays there are an enormous number of techniques being used to search for dark matter to basically try to find a way to do nuclear recoil discrimination. These have been developed over the last 20 years or so. And they combine, in general, two different measurements in a given target because you need two numbers to be able to separate an electron recoil from a nuclear recoil. Some experiments try to measure the ionization that's produced. So the recoiling particle, it's charged, it rips electrons off of atoms as it passes by them. And the amount of ionization produced is different for nuclear and electron recoils. Some of them look at scintillation light. So that's, again, electrons get ripped off, but then they recombine and emit light. Some experiments look at the acoustic vibrations that are created by the disruption of the lattice when either a nucleus or an electron is hit. And then there's a very interesting technique using bubble chambers where you take a superheated liquid that wants to boil but is kept liquid, but then if you deposit a lot of energy in a very small region, it'll create a bubble, and that won't happen for electron recoils, and it will happen for nuclear recoils. So different experiments use these different techniques to try to separate the two, and so I'll tell you about some of them now. So the one that I work on uses sound, uses phonons. So the idea is that interactions of any particle and target cause some sort of acoustic vibration. So in fact, most of the energy, whether it creates ionization also or scintillation also, most of the energy actually goes into creating sound or heat. And so you can try to detect that sound, and it actually provides a measurement of the total energy deposited, independent of the type of particle. So the way we do it is we take a crystal of silicon or germanium, a semiconductor, we cool it to about 40 milliK. So you have to cool it down to very low temperature so that there are no thermal vibrations left. So you can see the vibrations created by an interaction of a particle. When a particle comes in, it interacts, it creates sound waves, and those sound waves propagate around the crystal at about 1 centimeter per microsecond. So they reach the surface very quickly. Silicon and germanium are very stiff materials. And then we use some clever technology where we take a superconductor, so that's a material where the electrons have decided to pair up into something called Cooper pairs, and these sound waves are energetic enough to break those Cooper pairs. And then we can detect the Cooper pairs because we put a thermometer on the edge of the superconductor, and as the broken Cooper pairs fall in, they heat up the thermometer. And we monitor the thermometer's temperature by looking at its resistance, which is a very steep function of temperature at a particular temperature. So we sit here, and when energy comes in, the resistance goes up, and we monitor that. So thereby we detect the energy that was deposited in the crystal. This is done with sensors that are photolithographically deposited on these substrates. So this is an older generation where we use 3-inch by 1 centimeter substrates. And you can see here these large fins are the aluminum, the superconductor, and then these thin pieces are the thermometer, the tungsten. And then we segment that sensor into 4 quadrants so that we can get position and timing information. And it's actually pretty remarkable. These things really operate like microphones. If you clang cymbals in a room like this and you have microphones in 4 places, you can use the relative amount of sound you hear and the time of arrival of the sound to reconstruct the position. And we do that. So here's an experiment where we expose the detector to a radioactive source, but with a collimator, so that the particles were only deposited in 8 places. And you can see that by looking at the amount of energy in each of the sensors, we can reconstruct position. Or if you look at the relative time of arrival, you can reconstruct the position. And notice how small the time scale is here. Just tens of microseconds is the time it takes for the sound to travel to the surface. So we've been using this technique for about 20 years, and we've been constantly improving it to try to look for dark matter. So initially, it was a very simple system where we would detect the electrons and holes that were produced when a charged particle would recoil in the semiconductor by drifting them out with an electric field. And then we'd have phonon sensors on the surface. And so we would measure, the x-axis here is the phonon energy in keV. I apologize, I lost the label. And then this is the ratio of the ionization signal to the phonon signal. And we've normalized it so electron recoils are up here in this blue band. That's exposure to a gamma source. And nuclear recoils are down here in this green band. So if you're looking for these, and most of what interacts in your detector is this, you can imagine it should be very easy to look for these kinds of interactions and see whether you've seen WIMPS. However, we found there were problems early on that some of these events actually rained down into this region. And the reason that happened was because events that were very near the surface, we didn't collect all the ionization signal for those. And so we had to find a way to get around that. And we actually found a trick, which is that when you look at the phonon signal, an event that's near the surface has a slightly faster rising edge in the sound signal than one that's in the bulk. So now you can separate out these surface events and again try to look for interactions of dark matter in the bulk of the crystal. And then more recently, we've come up with an even more clever idea where we actually make the electric field in the crystal very somewhat complex, where if you're in the center of the crystal, it's still just a simple electric field that pushes electrons one way and holds the other. But then we have alternating electrodes on one side and the other side, so that if the event's very near the surface, some electrons go to these electrodes and the holes go to these ones instead of going all the way across. So then if we measure the signal seen on the top side, the bottom side and the top side, we can compare the two. They'll be consistent if we have electrons and holes in the bulk, but they won't be consistent if we have them near the surface. And that's what we see. This is comparing the side 2 charge collected to the side 1 charge collected. Here's bulk events which could be WIMPs in the center, and then these are the surface events, the ones that are occurring near the surfaces and we want to get rid of. So these are also nice ways to reject backgrounds. Okay, there are many other techniques for studying dark matter. I'll tell you about a couple of others of them. So another one is to use liquid nobles. And typically the way this works is you use the fact that in a liquid noble, so a liquefied noble gas, When a particle interacts, two things are produced. There's scintillation produced, which you can detect immediately by having photodetectors at the top and bottom of your liquid. And then electrons are also produced. And if you apply an electric field, then the electrons will drift up, and you can actually extract them from the liquid, have them avalanche in a gas region, and then they produce light also. So then you get a second pulse of light called S2. And the amount of the two of these is different for nuclear recoils and electron recoils. And so that's shown here in this data where we look at the ratio of the S2 light to the S1 light as a function of the S1 light. This is what you expect for electron recoils because this is exposure to a tritium source that produces electron recoils. And then this is exposure to neutron sources that produce nuclear recoils. And you can compare these two plots and see that the nuclear recoils are separated from the electron recoils. They would be down here if you were looking for WIMPS. So you have, again, another way to separate the backgrounds that produce electron recoils from the signal that you expect, the nuclear recoils. Another nice aspect of at least the heavier liquid nobles, like liquid xenon, is that they're so dense and they have such a high Z that they're actually very good at stopping background. So this is a profile of the event rate seen in one of these detectors as a function of radius squared and height. And you can see that out near the edges of the detectors, there's a large event rate. That's contamination from the outside. But as you go toward the center, that contamination gets stopped. It's getting absorbed so that the center of the detector is very clean. And so you can get rid of these backgrounds and try to look for WIMP interactions here in the center of the detector, and that's what's done. I'll skip this, it's very similar. Another technique is to use bubble chambers. So what's shown here is nucleation of bubbles in a superheated liquid by neutrons scattering off of the liquid. Let me run it one more time. Oops. So you can see those bubbles forming. What's happening here is that the liquid's been put in a state where neutrons that create nuclear recoils have a dense enough energy deposition that bubbles can get created. But if an electron recoil gets created, its energy is spread out over such a large region that it will not create a bubble. And this rejection is actually enormous. So this is the probability that an electron recoil will nucleate a bubble. And you can see that it's getting down to 1 part in a billion or better at thresholds that are interesting, a few keV. This is data for one liquid, CF3I. This is data for another liquid, C3F8. Okay? But this experiment found that while they're very good at rejecting electron recoils, they actually get a lot of alpha decay. So alpha is a daughter product that comes out from radon. So they found that their vessels were contaminated, and they found that they were just getting radon into the liquid, and the radon would decay and create alpha particles. So they came up with a clever idea, which was to listen to the events. So they put piezoelectric transducers around the vessel, and they found that events due to alpha particles are just louder than events due to nuclear recoils. So these are the nuclear recoils here. These are the alpha particles. So by combining the rejection of electron recoils using the whole bubble chamber idea, and then listening to the events to throw away the alphas, they can now search for nuclear recoils from dark matter. So this is a very clever technique. Okay, and now let me tell you about a couple of the kind of most interesting techniques that come from our motion in the galaxy. So one is called annual modulation. So the dark matter in the halo of our galaxy is moving presumably isotropically for the most part, just zipping around in all directions. But the disk of the galaxy rotates very coherently. So in particular, the sun is moving around the center of the galaxy at about 270 kilometers per second, or 232, sorry. And then the Earth is moving around the sun at about 30 kilometers per second. We're tilted about 60 degrees from the plane of the galaxy. So if you do the sine of 60 degrees, you get 15. And that means that depending on time of year, either our velocity is 232 plus 15 or 232 minus 15 relative to the galaxy. But the WIMPs are sort of isotropic with respect to the galaxy, so therefore they're coming at us primarily from one direction. And in particular, because of this change in our relative velocities, the velocities of the WIMPs in the lab looks different depending on the time of year, and they produce a spectrum of either more energetic or less energetic recoils depending on time of year. So that's what's shown here. The rate of recoils as a function of recoil energy, it's a harder spectrum, a spectrum that goes to higher energy in June, and a softer spectrum in December. And so there's an experiment called DAMA that's attempted to detect this effect by looking at the modulation of the counting rate in their detector as a function of time of year. And in fact, they claim to see a modulation that's stable over many, many, many years. This is around 10 years, I believe. And it actually turns out to have about the phase that you'd expect for dark matter interactions from our galaxy. And it actually has a shape and energy that's what you'd expect for kind of a typical WIMP candidate. The problem is that no one else can reproduce this. But you have to be a little careful because no one else has run this experiment. No one has used the detectors they use. They use sodium iodide scintillators, which most people don't want to use because it's actually not a very good dark matter detector. It has very little ability to discriminate nuclear recoils from electron recoils. All it has is the ability to buy a lot of it, so you can do an experiment like this where you see this very small modulation. This modulation is only a few percent. So no one's reproduced this experiment up until now, and so you can always invoke something like, well, maybe dark matter interacts in a special way with sodium and iodine and not with other elements. But now finally, there are a couple of groups that are trying to test this, given that this signal's been around for so long. So one is called DMICE, and what they're doing is they're taking sodium iodide crystals, except they're going to put them in ice at the South Pole, and they've actually demonstrated that this works. And the idea is that if the signal that's being seen here is due to some sort of environmental effect, for example, the number of muons passing through the laboratory in which this experiment is held changes depending on time of year because the atmospheric pressure above the laboratory varies with time of year. So if this is due to some sort of annual effect that's due to weather, et cetera, then if you go to the southern hemisphere, you should see it change phase. So they will try to test whether they see the same phase of signal or not. And then there's another group that's actually said, let's try to make the detector better. Let's try to get better, lower radioactivity sodium iodide so then we can be more sensitive to this kind of signal. And so they've done a very good job. This is the background spectrum that the annual modulation experiment sees, and then this is what this new experiment expects. So a factor of a few improvement, which makes them more sensitive to this type of annual modulation effect. So hopefully we'll get to see in the next few years whether this result can get tested. Okay, and then there's one final effect, which is very interesting, which now has to do with, again, the motion of us, of the Earth in the galaxy. And now it's due to the fact that the Earth rotates. So as I mentioned before, because we're moving relative to the dark matter, most of the dark matter appears to be coming from one direction, and that's actually the direction of the constellation Cygnus. And of course, the direction of Cygnus rotates in the sky as a function of time of day, whereas most of the backgrounds, the stuff that will interact in your experiment and might cause a fake signal, will not. It'll be constant with time of day. So if you're able to measure the direction of the recoiling nucleus, that direction will always be in the hemisphere away from Cygnus. And so you can try to look for this, what's called diurnal modulation, the fact that the direction will be modulated in the lab frame, and try to detect this particular signature of dark matter. And the way to do this is by making an image of the track of the recoiling particles. So here's a diagram showing if a dark matter particle comes in and hits a fluorine nucleus, the dark matter particle scatters off, but then the fluorine creates a track. And this is, of course, in a gas. In the liquid or solid, that track is only tens of angstroms long. But in a gas, that track can be millimeters. And what you can do is you can apply an electric field and drift that track down to then a place where it can, you can image that track by causing an avalanche and detecting charge or detecting light. So you can create images of the tracks of the particles, and then you can see what direction those tracks point. And so there are two experiments that are trying to do this. The problem is that currently, because you have to use gas, you can only get about hundreds of grams of target material in a cubic meter chamber, whereas many of the experiments I've talked about can get 100 kilograms of mass in a chamber that large. So this is not a good technique for trying to detect dark matter the first time, but it will be a good technique for trying to demonstrate that what we've seen is really dark matter because it has this diurnal modulation effect. And so there are two experiments that are trying to do this, and they are currently scaling up to kind of cubic meter, couple cubic meters type experiments here. These are some CAD drawings showing what they're expecting to do very soon. Okay, so let me close by kind of talking a little bit about the future. So I've talked primarily about directly detecting dark matter by seeing it scattering off of nuclei, but we really need to see dark matter in three different ways. We need to see that we can produce it at an accelerator in multiple ways that are consistent with each other. We also hope that we see it annihilate in the sky and produce products that we can detect, and again, multiple products that we can see can be consistently interpreted in terms of dark matter. And then we would like to see it directly detected in multiple targets, so not just germanium or not just silicon or not just xenon, but in multiple targets with consistent properties. And then eventually we'd like to build this directional detection experiment where you see this unique diurnal modulation signal. So it'll tell us about how dark matter couples to normal matter particles, but it'll also tell us a lot about the halo of our galaxy. It'll tell us about the density and velocity structure of the dark matter. and what the dark matter abundance is in our galaxy. And is it enough? Does it actually explain all the mass that we need in order to explain the speed at which stars and gas move around the center of our galaxy? So this is sort of the program for the next 10 or 20 or perhaps longer years, I hope it's not that long, for detecting dark matter and showing that it really is the dark matter that we need to explain what we see when we look at the sky. So there's a lot of work to do, and I'll stop there. Thanks. Questions?
Comment on the excess high-energy gamma rays observed by the Fermi Gamma Ray Telescope in the center of our galaxy?
Right, so the question was asked about the excess of gamma rays from the center of our galaxy seen by the Fermi Gamma Ray Space Telescope. So that's this technique back here, where you have dark matter particles annihilate, and in this case, go back. Yeah, okay. Where you have dark matter particles annihilating and producing gamma rays. And so what's been seen is an excess that is consistent with it being dark matter and not dark matter that's been ruled out in any other way. The issue is just that this is a circumstantial evidence type of thing. You see this spectrum of signal, you say, okay, that is consistent with the dark matter model, but it can also be explained by a few different astrophysical sources. And so the problem is that you don't have the smoking gun yet. You have something that's indicative, but not the smoking gun. So what you'd hope to see is maybe a couple of these other indirect signals that are consistent and point at the same mass dark matter particle candidate and same annihilation rate dark matter candidate. It would be really nice if you could see that candidate in the lab with a direct detection experiment. So there have actually been about, I can't remember off the top of my head, but no more than 10, but more than 5 claims in the last 20 years of seeing dark matter from annihilation from various space observatories. So until you see it in a couple observatories, it's unlikely to, that it'll be taken too seriously. So. Other questions?
I was wondering, from a philosophy and science standpoint, you said that maybe now you have enough evidence that you think you're sort of converging on direct evidence for the WIMPS. But the first thing that you said about the primordial black holes was that they were not well motivated. And I'm wondering, why are the WIMPS better?
Well, the WIMPS tend to be a better model because you can come up with particle physics models that have other nice properties that explain other nice things that also predict WIMPs, whereas for primordial black holes, it's not a very predictive theory, right? You just posit that these things got created in some way. There's not really any way to predict what the mass they should have is, why there should be a certain density of them. So it's an explanation, but it's not a particularly satisfying explanation. But that... Yeah. Well, as far as I know, there are no predictions for primordial black holes that are truly predictive in that sense. People have looked for them. You'd expect that they would actually produce gamma rays when they slowly evaporate over time from Hawking radiation. So people do searches for these things using gamma ray observatories. But if you asked how many people search for those things versus search for WIMP dark matter, it's many more that look for WIMP dark matter. And so that's just a measure of how motivated people think one idea is or another idea is. Other questions? Yep.
Could you summarize again why this matter could not be ordinary matter like neutrons or very diffuse hydrogen or brown stars that just are not visible?
Right, okay, so the question was, why can't this be normal matter? There are a couple of lines of evidence, and I didn't talk about them in any detail. One of them is that you can measure the abundances of light elements, and you can trace this back to the nuclear reactions that happen in the early universe. And the abundances of light elements basically tells you how many total baryons there are in the universe. If there are more baryons in the universe, so baryons being protons, neutrons, all the normal matter, that affects these light element abundances. And they're very consistent with about 1/6 of the total matter being in this normal matter, 1/6 of the total matter being in normal matter. But I think that's it's an astronomical measurement that's a little hard to make. There's systematics in it. I think the most compelling evidence is actually from the microwave background. You simply can't explain how you got from the microwave background, which has fluctuations of a certain size, to the structures we see today if there's only baryonic matter, if there's only normal matter. The fluctuations just weren't big enough. You need to have something else that was already collapsing at the time that the microwave background was released so that you can form the structures we see today. Okay, I think we don't have time for other questions, but I'm happy to answer up here afterward. Thanks very much.